So thanks for this opportunity to share my work on our ranking model. And so in this work, we proposed a new Partition-Mallows model to do the rank aggregation. So here's the outline of this talk. So first of all, I'll give you a brief introduction of the problem. And then
Andy,
we do some. Yeah.
Andy, I think we're seeing just we're not seeing your full screen mode, so you might have to switch just what you're sharing. We're seeing your Adobe, but we're not seeing the full. If you want us to see the full, are you trying to get us to see the full screen mode? We're not seeing that one.
Yeah, we're not you're not scrolling through the slides. Andy.
No, we're not scrolling through the slides for us.
Okay. Is it better now?
Yep.
Yep, that's it. We got it.
Okay. Just use this mode, I guess. So there's, okay, so you can see it, right? So the second section will be the literature review, and then we'll talk about the new model. We call it PAMA model, and also its inference. So in section 4, I'll give you some simulation results, and then followed by some real data examples. Finally, we conclude with a discussion. Yeah. So introduction. So the problem of rank aggregation is quite actually simple formulation. So now in this table, we have 5 rankers. So you can see that there's 5 people there. And then we have 10 entities. We denote that by A to J. So every ranker can have a rank list of these 10 entities. Then now we have 5 rank lists. So the aim of the rank aggregation is to get just single rank list based on this 5 rank lists, and then we can have hopefully we can get this single rank list which is better than all of them. So it seems like we borrow the wisdom from individuals and then make it better. So this is a problem of rank aggregation. So in some real data here, so we have this NBA teams power ranking. So now we have 6 professional rankers. They're both maybe experts of basketball from some very professional website. They provide the rankings, and also we may have some some surveys from some basketball fans. They may provide the full rank list. Also, they may just provide the top K rank list. So generally, this is the data we are going to work on. Then from this table, we are trying to get a single rank list. This problem actually is a very old problem. It could be dated back to 18th century, which is very popular to get some voting social science. So you get the voting for different candidates, and then you combine them, get a single result of the final results. So one naive idea is to use deterministic approaches, such as you get summary statistics based on the data. You can use the mean or median for robustness, or geometric mean. So the idea is still we have 5 rankings of 10 entities. Then you can compute the mean or whatever, or geometric mean. And then based on this mean, you can get the aggregate ranking. So this is a very naive idea. And also, you can change this problem to be an optimization problem. You define some objective functions because the talk here is data. So if we have some distance measurement, so the final aggregate ranking should be minimize the total distance from the data. So there could be different distance measurement. So this problem is transformed to be a optimization problem. Also, there are some probabilistic models to model the ranking data itself. So the most popular one, I think, if you have attended the presentation from Jess, she gives this very similar like model. She uses this, I think, is the Plankett-Luce model. So both of these models are very popular probabilistic models to model the ranking data. So both of them have some logic to follow. But from the literature, we found there is a problem which is not fully solved yet. So that is people generally don't consider the quality difference between the rankers. So the question is, so the existing approach assumes that each ranker, all the rankers are equal reliable. But I guess in practice, that's not very practical. Here, just give you a sense of the quality difference of the rankers. So here, we have 20 entities and 6 rankers. If you look at the data more carefully, you will see, here I just use the red color to highlight the rankings which is less than 10 for the first 10 entities, because the true, we seem like this data, the true ranking is 1 to 20. So if there are more red numbers here, that means the ranker is more reliable because it's more close to the true ranking. More quantitatively, we can compute some distance. Here, I just use the Kendall-Tall distance. So for each row, we compare this ranking list to the true ranking. So here's the distance. From this distance, you can see the first 2 rankers are very poor quality rankers. And for the other 4 rankers there, we say that it's good quality rankers. So if we just only use the mean of this data, so this last row, we just use all of the 6 rankers to compute the mean, and we get the final aggregate ranking, and then we also compute the distance with the true ranking.
Sorry,
but now,
is that the mean or the median? The median?
It's a mean.
Right.
Yeah.
Okay. So
it's a mean.
If you go back, so it's the mean of the first column, right?
Yeah.
I sort of, with that's 10, 13, 2, 1, 2, and 2, right?
Yeah. So you get the mean and then you rank the means.
Okay. All right.
You sort them, I guess.
Yeah. Yeah. Yes. Okay.
Yeah.
Yes. Okay. I understand. Thanks. Yeah.
Andy, can I ask a question? The distance, is it the same? So each entry here affect the same way to the distance? So if you're missing on the first 10, is it the same as missing on the last 10, or is there some sort of weighing of that?
This value?
Well, just what is the effect when you kind of look at the rank and compare it to the true one? Does it really matter if the order matter, but is where you miss is more important, or is it just in general how well you kind of miss that?
I think the distance is more important. If the first ranking list is very far away from the true ranking, that we generally say it's a bad ranker. But up to now, we don't know how to quantify the the badness or goodness yet. Hello, Gilad. Does that answer your question?
Yeah, thanks. I did with the finger like that, but thumbs up, but can't see that.
Okay, yeah.
Thanks.
So yeah, from the distance, we can say there are 2 per rankers, but we don't know how to measure it yet. But if we just cross out the first 2 rankers and also compute the mean, and then we get this green results, and we compute the distance with the true ranking. Then we compare the previous results, then we get something better, right? So the problem will be, how do you know the first 2 are bad or good? How do you measure that? Or make it, to do it in an elegant way to do that. So there are also some research already focused on that problem. So possible solutions for the quality difference. Based on the optimization problem, then people just propose a weighted optimization problem. Then they just change the objective function to be a weighted objective function. Then, but you don't know how to assign the weights yet. Also, there are some others like this one. They just split the entities in 2 groups, and also there is some extended Mallows model. But they don't fully resolve the problem yet. So we propose a PAMA model here. So the motivation of the new model here is, in many scenarios, people only care about the top K entities and their rankings. And also in this new PAMA model, we don't need external information to quantify the reliability of the rankers. So the model itself can distinguish the reliability of the rankers. So for the first point, so people only care about the top K entities. For example, in this data, so still the NBA team's data. Although we have the full ranking list, but people may only care about, only the first 16 teams will enter the playoffs. So people may only care about which ones are the first 16 teams. So they only care about the top 16 teams. They don't really care about the others, right? So there are other scenarios, people only care about the top K entities. So that's one of our motivation to do the partition model. And also, when I say the partition model can review the reliability of the rank itself, it means here. So if still we have the 10 entities, but the first 5 is relevant and the second 5 are background entities. So if we split these 10 entities in 2 groups, a good ranker, a typical good ranker will be no mixing between these 2 groups, something like this. So it could be some missing internally in each group, but they don't have, generally they don't have the mixing. So that's a typically good ranker. But a typical bad ranker will be, they just mixed up a lot. So for example here, so like this entity 9, they have ranking 2. They just mixed with relevant entities. So with this idea, we can use a partition to measure the reliability of the ranker. So this is the 2 motivations of the model. So now I just formally introduce the model, PAMA model. So the entities, there are n entities. We get the relevant entity and the background entity. The relevant entities, there will be N1. That's the number of relevant entities. So we have M ranking list. So now the problem will be, we find the group indicator I. So the I will be some 1 to N1, and for the background, we just say the zeros. So we have also the quality parameter of the ranker, we denoted by gamma 1 to gamma M, and there are 3, the relative ranking of the relevant entities. We use tau 1. And the relative ranking of background entities, I use tau 0. And also, like we just talked about the mixing. So right, so we use a tau 0 given 1 as to measure the mixing between these 2 groups. So this is notations I will be used in the rest presentation. So the data generation process, and after you have understood this data generation process, you may have the better understanding of the model itself. So there are 3 procedures, three steps. So this is the true rank list. We generate from this true rank list, and we have other parameters. So according to tau 0 here, so we rank the relevant entities. So that's the good entities first, via some Mallows model or some other models. And then we generate the relative ranking of the background entity among the relevant entities. So that's the mixing of the bad entities among the good entities. Then permute the background entities via some distribution. So more visually here, we have 10 entities and 5 good ones and 5 bad ones. So this is the underlying truth, the ranking list. So we can use some model here, just to rank the good ones. And then we can use some other distribution to model the tau 0 given 1. So that's the mixing part. And then we have this tau 1 and have this tau 0 given 1. Then we can combine these 2 to be a full ranking list here. And also because here, both these 2 are 1s, so they could be used some other distribution to sample these 2. So finally, we got this samples of the model. Anyone have any questions so far? It's all good.
I just didn't get the part that you said what is good or what is bad. So what makes those two colors good and bad?
This one.
Yeah.
So,
Wasn't relevant.
yeah. So a typical good ones, that means if you have this orange color, which is bad entities in general. So if they don't, go up to mix with the good entities, so that ranker is a good ranker.
Sorry, I didn't get it again. Can you repeat?
Yeah, because this is a true ranking, right?
Yes. So okay. So that is true ranking.
True ranking.
Yeah.
We have two groups: the good ones and bad ones.
So what is good and bad ones?
So good ones means the top, because
Only
it's ranking
just
fine.
the top 50%. You call it relevant.
Yeah, you can define the cutoff line.
Yes.
Yeah. So a good ranker, they just don't put the bad entities up to the good ones, right? So for example, here, all the orange ones, they just ranked as 6, 5, 7 or something. They're all quite similar to these true rankings. But here is a better ranker. Better ranker means they, like this, they rank the entity 9 to be 2, right? The ranking is 2. And here is 4. So they just rank the better entities with very high ranking. So that means generally it's a better ranker.
Yes. Okay. Thank you.
Yeah.
So just
So-
another question.
Yeah.
Sorry to interrupt. So when you're combining the relevant ranker and also the background ranker, how do you combine these two? Like, how does the false column, like, how do you construct the false column here?
Yeah. So here, so say for this one, the 10th entity here, because the tall 0 given 1 equals to 1, right? So that means, so this entity is this never goes up to the good ones. So this at the end of this good ones. So they have no mixing. But for this one, for this entity 6, the p tall 0 given 1 equals to 3, that means there are 2 good entities ranked below this entity. So here you can say here, finally it's ranked 5, right? So there are this one ranked 6 and this one ranked 8. So there are 2 entities, 2 good entities is ranked below this one.
Right, makes sense. Thank you.
Yeah. So the big value here means there are more good entities is ranked below this entity. Yeah. So given these 2, tall 1 and tall 0 given 1, you can combine them together to be a full ranking list. So in this figure, I just specify this model part 1, part 2, and part 3. So I will give you more information about these 3 parts separately. So the model 1, I just use the Mallows model, which is quite well-known model for the full rank list. They have these densities and they have the very straightforward interpretation And also people just generalized the Mallows model to be more general case. And for this very recent paper, they proposed another very generalized Mallows model. So the Mallows model will be used as the model part 1. So model part 2 here, because here means the relative ranking of the bad rankers in the good rankers, in the good, bad entities in the good entities. So the desired property for this part 2 is the higher quality the ranker is, the less mixing is. And also given the quality of the ranker, the probability of mixing is negatively correlated with severity of mixing. So in other words, that means if a ranker is a very good ranker, we want the mixing is 0. They don't have any mixing. And if the ranker is a very bad ranker, the mixing is very, there is a lot of mixings between the good rankers and bad rankers, good entities and the bad entities. So what does that mean? So suppose we have the 3 good entities now, and the 4th one is a bad one. So if this tau 0 given 1 equals to 1, so the entity 4 will be at the end of these 3 entities. There's no mixing. What? If the mixing, if this value equals to 2, that means there is 1 good entities is ranked below this entity 4. That means the final ranking will be 3. So you get the sense now, right? So if this value is very large, so the mixing is very severe. And if this value is equals to 1 or is very small, there's no mixing. So that's the distribution we are trying to look for. So we just use the power law distribution to model the value of tau 0 given 1. So this distribution satisfy all the requirements we're trying to find. And we did some simulations using the power law distribution. This linearity means that this power law distribution is quite good approximation of the true reality. So this is model part 2. And also now we are going to find the model part 3. So the model part 3 describes the distribution of background entities. So we use a uniform distribution because we don't care about the rankings of the background entity. So basically, we give a Mallows model for the good entities. We have a power law distribution to model the mixings, and we use the uniform distribution to model the background entities. So yeah, this table shows how to decompose a full ranking list to be the 3 components, and then you can combine the 3 components to be a full ranking list. So they're equivalent. So now the model, so people just usually just directly model the full ranking list, but in the partition model, we model these 3 components separately, and we have the properties we designed. So, okay, so this likelihood function of a ranked list can be decomposed into 3 terms. So this term is Mallows part. This is power law distribution, and this part is uniform distribution. And the full computation of each part is quite straightforward. So Mallows model, power law distribution, and uniform distribution. So far, any questions? Yeah, all good. Okay, now assuming that the tau1 and tau-m are all independent, then we can compute the distribution of the whole observation, the whole data, because it's just a product of individual ranking list. And given this likelihood function, we can do either Bayesian inference or MLE inference. So with the Bayesian inference, it's just set the price for different parameters. So the parameters are phi and gamma k. And then we derive the posteriors. For the sampling part, we use Gibbs Metropolis Hastings samplings. So we derive the full conditional distribution of each parameters. And given the samples, we can always do the estimation by using this. So the ranking aggregation, the phi estimation of the phi, and the quality estimator is gamma. For the MLE estimation, we use the cyclic coordinate ascent algorithm. So it's quite similar with the Gibbs sampling, but they just update each parameters in turns. So just update gamma k. We have this modern condition distribution given other parameters, and we use Newton's method to update. And update phi, update the ranking list. Because this I is discrete, so we just use some proposal. We can't use Newton's method because it's discrete. So we propose some new estimation and then test whether the likelihood is increased or decreased. So with the rejection or acceptance. So this is MLE estimation. So this model, back to this the example I just showed you at the very beginning. So we have the full ranking list. We also have the partial list. So we extend the PAMA model to work on the partial list. So in the Bayesian inference, we use a data augmentation strategy. So it's similar to the EM algorithm. So so tau k is a partial list, and then tau k star denotes the corresponding full ranking list. So we just impute the partial list to be a full ranking list given the other parameters. And then with the full ranking list, we can still do the Bayesian inference. So this is algorithm for the partial list. And in some scenarios, we also have the covariate-assisted. So that means we have the ranking data, and also we have some features of each entity. So we use X to denote the covariance matrix, which is the features of each entity. So hopefully we can use this X to improve the accuracy of the ranking list of the ranking aggregation. So we incorporate data X here in the model. So we model X. So essentially, we just use this X to be a logistic regression to predict the membership of the entity. So this is logistic regression. For this model, we prove like the model identifiability and also the consistency. I just give you some scratch of the proofs. So in the identifiability, we just prove it start from m equals to 1. So there's only single ranking list. Then we use the mathematical induction method to generalize to be m to be any number. So this is for model identifiability. So that just for people who maybe don't know the model identifiability. So that means for any parameter vectors here, so the data given the theta 1 and theta 2, if they are equal to each other for any data, then theta 1 must be equal to theta 2. So so most of the models, they are satisfied with this model identifiability. But here for this partition model is not clear. So we just have to show the model has this property. And then another theorem we have proved to prove the moment of the estimate is converged to the true rank list with probability 1 as m going to infinity. And given this, we also prove the other parameters phi and gamma, they also converge as well. So these properties guarantee this model will work well in theory. And we also do some simulation studies. So we generate the data from 2 different settings. So the first setting will be the data is generated from the true model. We denote it as a scenario as PAMA, PM. And this, we use different parameter settings to denote different signal strings. We also use the hidden score model. So for the hidden score model, it does belong to the true model, but it assumes for each entity there's a hidden score attached to them, and then we use the hidden scores to get the ranking list. Just for one example, we have 10 rankers here, but for the first 5, both of them, they're just a random noise. They have nothing. They have no signal. But for the second 5 rankers, you can say the good entities, they generate the data from some positive mean value. And for the better ones, they steal from the mean with 0. And also the quality of the rankers will increase because this value increase. Because there is more gap between the good entity and the bad entities. So that means that in general, it's a good rankers. In total, we have this 16 settings for PM1 and PM2. We use M is number of entities, N is number of M is number of rankers, N is number of entities. And for different settings here, so this is a hidden score 1, hidden score 2. So we use these two criteria to evaluate the performance of the models. The coverage means N1 is the number of good entities. So the N tall hat means the good entities we detected by the model. So this means how many good entities we have detected in the model by using the model. This coverage. So the recovery means with the estimation of the ranking list, what's the distance between the estimation with the true ranking? So this measures the distance. And here's a table for the simulations. So we have 9 models here. The PAMA F is the MLE estimation. The PAMA B is vision version. This is BART, and the EMM and MM and other so MC-based algorithms. So for the different settings here, here you can see for the I just highlighted the best performance for each scenario. So you can see in general the partition tab models are doing very well compared to the other models, and most of the time the PAMA model is doing the best. This figure shows the quality estimation. Because as you can see, for this subfigure, for example, the first 5, the gamma is very small, which is very close to 0. That means that's bad rankers. And for these 5, the gamma is very large, and they're good rankers, and they have this increasing quality as well. So you can say the PAMA model can capture these qualities very well. They can capture this very well, and then they can distinguish the reliability of the rankers. Yeah. And this is just for one scenario, M equals to 10 and N equals to 100. So we have the this is coverage, and also this is the gammas for different model. This is PAMA B, PAMA F, BART, EMM, and EMM. So yeah, so basically just show the more details about the results. So it shows the similar pattern of the rankers quality, and also here shows there are more details about the coverage as well. And also we did some simulations to test the robustness to the specification of N1. So previously we assumed like we know the value of N1, but here I just simulated data and we don't know the exact N1 is. There's no clear cut of the N1. So just run the model with N1 equals to 10, 20, up to 50, and compare also the similar criteria, and say here, so the PAMA model is also the best, or almost always the best. So that means it's quite robust with respect to the N1, where there's no clear cut about the good entity and bad entities. And here I just plot the average rankings of the top 10 entities. So when you increase N1, so the top 10 entities are quite reliable. They're always captured by the model. And here just show the box plot of all the entities, and you can say the true N1 is equals to 10, but this graph is obtained. We set the N1 equals to 8, and this we set the N1 equals to 10, and this one we set the N1 equals to 18. For all of these three scenarios, we can see the first 10 entities, like posterior sample, are quite separated with the others. So that means, so that the PAMA model is quite robust with respect to N1. So they can always distinguish the first 10 and with the other bad entities. Okay, so here is the real data analysis. This is MBA team, and we run the algorithm. We get the first 6. Here you can see it's clearly the gamma is larger than the others because it's professionals, and also this full ranking list. For the others, it's just from some basketball fans, they only provide some partial rankings. And we use some surrogate truths to compare the final results, and the PAMA model is slightly better than the others, the other two. And also we use the NFL. This is the rankings of the NFL players, and also they have some features of each player. So we can incorporate that features into the algorithm. And this is the result, the posterior sample. So, and we also compare, we find some golden standard, and we compare with some other algorithms. So PAMA is slightly better than others as well. Okay, so the main takeaway is PAMA can deal with the heterogeneous quality of base rankers. So we can deal with like different qualities of the rankers. The PAMA provides the detailed rankings of the good entities. And also PAMA can be applied to the partial ranking list, to the feature, to the features as well. And also the simulation shows PAMA is good in general, and it's robust to the specification of N1, and works well in the real data. Yeah, that's all. Thank you very much.